Hey, what's up, guys? Okay, so in this video that I'm gonna to talking about the idea called the Martingale. So this is I recently started some financial mathematics and probability theory. I think it's interesting. So I will do some like 3 exercise to proving some function continuous variable continuous function like Brownian motion and however some of them are Martingale. And just this one will connect it to that previous the Ito lemma and stochastic calculus. You can check out my video list. Okay, so this is what we're gonna do talk about is Martingale. Okay, so sometimes it's hard to understand, but I finally understand what this idea is talking about. Okay, so let's talk about definition. So discrete version. So a discrete version, let's say you have x1, x2, x3, all these are random variable. Okay, so if you're like some very theory guy, you can start from some probability space. So basically you can some set, finite countable set, and then you can create some f, which is a so-called sigma algebra. And then you have some probability function p. Okay, so some measurable function. So if you are like some guy which very theory, you can talk about this, but it doesn't matter. Okay. Let's say you have x1, x2 up to x, keep going. And so we require if the first one is that the expectation value of xn is less than infinity. And the second one, this one is simple, it's just well defined. And second one is that if you want to ask what is the probability of xn plus 1, let's say given you know x1, x2 up to xn. So this means that you already fixed the previous n number, right? So you just say your x1 is something, x2 is something, xn is something, and the expectation of xn plus 1 will be xn. Okay, so this equation is hard to understand if you need to think a little bit. But basically the idea is that there are some possible choice for x1 and another possible choice for x2 and then maybe another choice for x3. But up to xn, right? Let's say you already know this is the answer. This is the let's say this is the xn value that you observe. Okay, so some very technical terminology called filtration, but let's say forget about this. Then the xn, right? And then you want to know the xn plus 1. So there are a lot of possibility of xn plus 1. But all the expectation or value of xn plus 1 need to be the same as xn. So given x1 up to xn, the xn plus 1 expectation value need to be the same as xn. Okay. And then we say this sequence, this discrete variable sequence forms a Martingale. Martingale. Okay. And so let's maybe do some very simple example. So one trivial example, which is trivial but still non-trivial. Okay. Called random walk. Random walk is very, very interesting. That I think I make a lot of video about it, but probably different topic with equal probability. So basically means that somebody start from 0 and then they go half with a probability half. Okay. So obviously that if you ask the position as a random variable, right? So you start from x1, let's say x0 is 0, and x1 can be plus or minus 1, and x2 can be also can be maybe 2 or 0 or -2, right? Keep going. But obviously that if you know xn, all the xn, let's say xn is something called a, then the expectation of value of xn plus 1, given you know all of this, is basically a, right? Because you start from a, and then you go, you probability half, so a plus 1, and this is a minus 1. So if you calculate expectation value of a minus 1 and a plus 1, then it's basically a. Okay. So this is a fairly simple definition. Okay. But so usually if you want to prove something is continuous, something is discrete variable, which is Martingale, you can just directly apply this second, right? So this one can be calculated. Okay, but sometimes we can talk about the Martingale in a continuous version. So this one need to be required like more work. Okay, so continuous Martingale. So the continuous Martingale usually, right, the definition just goes as this, right? Let's say you have some stochastic process ST. So this is stochastic process. So stochastic process just means that each continuous variable, each t, give you a random variable. Okay. And what you require that say expectation value of let's say xt. Let's say given you know all previous time, right? So you know s. So for all s less than equal to t. So basically you know all of this. You know all the previous time. Let's say stock price or whatever. This will give you the same as ss. For all s less equal to t. Okay. So our base notation. So this is let's say tau less than s. Sorry about this. So let's say you pick tau. The tau is a variable which is less or equal to s, and you pick for all s less or equal to t. Then this is true, right? Obviously, that when tau equals to t, sorry, when pick s equals to 2, this will be trivial, right? But right, okay. So this is like a one-line definition, and obviously that we also require that the xt need to be finite for t. Okay, so let's say some example. Okay, so the first example, which is like some homework exercise that people like to maybe it's some stupid homework exercise. Let's prove that Brownian motion is Martingale. Okay, so proof is just very simple as required by your definition, right? So usually starting with mathematics, you should start from definition. Once you know definition, and you try to prove definition, right? If your definition is not good, then you try to develop some theorem to help you prove something is hard. Some to prove something, but this kind of should start from definition. Okay, so let me just quickly define require remember recall the Brownian. So let's say xt is Brownian. It's Brownian. If the first one is, I think, is the x0 start from 0, and right in the it's continuous, right? So this t is continuous, and you require that given xt, which is n of 0 t. So this is the Gaussian variable with variance t. Okay, and the number 4 is very weird. Let's say if you start from 0 and t, and you just t1, t2, t3, you partition to be tn minus 1. Then all this xt1 minus x0, xt2 minus xt1, up to xtn minus 1 minus xtn minus 2, and xt minus xtn minus 1. So you consider all these are independent. Sorry. So the third one should be, let's say, xt minus ss, right? So it should be n of 0 t minus s. I think yeah. So all this 1, 2, 3, 4 is called a Brownian motion. Okay, so one interesting is that theorem. This theorem is very hard. Basically, the Brownian motion exists. Okay, so I just want to point out that this is fairly very non-trivial, because it's unlikely that you define some very complicated rules and that rule will give you some really exist function. It's not very obvious how to construct such a ST, right? But in this video, let's assume the Brownian motion exists. Okay, so let's prove the Brownian motion is Martingale. Okay, so this proof is trivial. Okay, so what you want to prove is that its potential value of xt is a given the ss. So let's say ss. Let's say you know all these s. Sometimes we'll find f of s. So this is called filtration. So basically, if they say you already know that some time s previous some time s, all the previous s. You already know it. And then you want to show this is ss, right? This is the goal. Okay, so simple, you just write as xt minus ss plus f of s, so as plus expectation value of ss fs, right? And what's this? So since xt minus s and all the time before s are independent, right? This is the definition. So these are random variable of 0t minus s. And then if you take the expectation value with it, you get 0, right? Because these are independent of the previous information. And these are the Gaussian variable with mean 0. So you get this equals to expectation value of ss fs. So this turn out 0. And this means that you know the answer up to fs, right? So and as xs, you know the answer, right? So it will be ss, because you already know the information filtration up to s. So these are very important equation. Up to fs, then you go xs, then you give you ss. Right? Basically, this is the definition of filtration. Okay, so now we prove the Brownian motion is Martingale. Let's say second example. Okay, so this example is very simple, also fundamental exercise. So let's say you can define random variable is called mt, xt minus xt squared minus xt. Okay, so mt is Martingale. Okay, so usually if you know the stochastic calculus, if you know the Ito lemma, then you can prove it by just do the differentiation respect to this. So you can take 2xt dxt minus dt, right? So this is the usual derivative, but stochastic calculus will create another variable, which is plus of half of the second derivative of it. So you get 2 dt. And you can see dt canceled. So you get 2xt dxt. So you can see there's no other terms. So in this case, that if your differentiation has no other term, this will prove it's Martingale. Okay, but this is if you know Ito lemma, right? But let's say we want to prove by definition. Okay, so let me just do it one time. It's stupid, but play around with it. Okay, be sure to subscribe to my channel. So let's say this is fs. How do we do this? Doing the stupid trick as we just proved. Xt minus ss squared, right? So let's say you get minus, let's say plus 2ss minus s squared minus t fs. Okay. Well, and so this term with this, let's say we expectation value of x at t minus ss squared fs plus 2 expectation value. Let's do it again, right? Let's say doing st minus ss plus, so we get ss squared, right? 2. So we should add it, right? So we get expectation value of ss squared fs minus t. Okay, so this guy just constant, right? Constant just pull out the expectation value. Okay, so this is the 0 t minus s with the second moment, right? So this is t minus s plus this is 0, right? Because these two are independent, and this guy is 0 t minus s. So these two are independent variable, so it's 0. This term is ss squared, right? By definition. So we get ss squared minus t. So we get xs squared minus s, which is exactly what we're going to prove. Okay, so proof. Okay, and let me just go from the final example. This example is also another like homework people like to do, and I will do it very quick. So example 3. If you define another variable called yt, which is exponential theta xt, minus half of theta squared t is Martingale. And you can prove it by stochastic calculus from Ito lemma. Very simple. But I want to prove it, let's say yt fs. Okay, so what should I do? I should do the same thing, right? I should do always the trick. Let's write as st minus ss plus half of squared t. Right, and plus theta ss. So notice that now these and these are independent, right? So its potential value I can separate into two terms. Let's say filtration. And then this will be its potential value of theta ss, right? And for this term, these are just Gaussian 0 t minus 1. So this is the moment function of Gaussian, moment generating function of Gaussian variable, right? So moment generating function of normal distribution. So you write down a definition and times this, then you will prove the results. That's it. Okay, so you just write down the moment generating function of the Gaussian. That's it. Okay. Okay, so hopefully this example give you how to prove something's Martingale and give you some very simple definition of Martingale. And there's a very weird results called maybe next video or whatever. There's a theorem called option theorem. Option theorem. And there's an idea called stopping time. Okay, so this is a very weird theorem that about this Martingale. So this Martingale has some weird property that you can try to prove. I will try to prove it in next video. See you guys.